chapter on gases, and we're starting section 3 now. So there's 3 laws, it's actually 4. We're going to talk about 3 laws that that we'll use to solve problems simply. And they're Boyle's Law, Charles' Law, and Avogadros Law. And let me show you what those laws are. Those laws are, Boyle's Law says that pressure is reciprocally related, directly proportional to volume. Okay? In other words, as pressure goes up, volume goes down, or as volume goes up, pressure goes down. That's what that means. Another way to say that is we could say that pressure is equal to the reciprocal of volume times some constant, which I'm going to say K1. Tro doesn't use this language right here, but I think it's helpful to think in terms of constants. So let me say K1. We're not going to need to solve what K1 is. Mostly we're going to say that if that's true, then pressure times volume is equal to K1, right? And I'm going to derive all these, and then we're going to talk about them in more detail, okay? Pressure times volume is K1, or we could say that the pressure in the initial situation times the volume in the initial situation is going to equal pressure in the final situation times the volume in the final situation, right? Because if these are both equal to K1, then we could say P1 V1 is equal to P2 V2. Okay? Let's do the same thing with Charles' Law. Charles' Law says that, what is Charles' Law? I think Charles' Law is volume and temperature. Okay? Charles' Law says that volume is directly proportional to temperature. In other words, as volume goes up, temperature goes up. As temperature goes up, volume goes up, right? This is the same thing as saying volume is equal to temperature times some constant, which I'm going to call K2. Again, making up these things here, okay? Now, if that's true, then we could say K2 V over T is equal to K2, right? And you see what I did here? Divided both sides by T. And then we could also say that this would imply that volume in some initial situation over temperature in some initial situation is going to equal a different volume related to a different temperature. Okay? That's Charles' Law. Okay? And Avogadro's Law says that the number of moles is reciprocally related to, rather directly related to a volume. Okay? So, and if that's true, we could say that the moles is equal to some constant, K, let's say K3 times volume. All right? And then, let me do the same thing I did for these guys up here. Let's say, all right, well, that must mean, or that would give us the freedom to say that N over V is equal to some constant. And if that's true, we could say the moles in some initial situation times the volume, times the volume in some initial situation is equal to another situation where we've got a different number of moles and we'll have a different volume. Okay? So this is Boyle's Law, this is Charles' Law, and this is Avogadro's Law. Okay? And let's develop those now individually. So before I do, let me tell you that Robert, I'm just reading Tro to you right now, okay? Tro says in the text something pretty interesting. In the 1600s, Robert Hooke and Robert Boyle, Boyle was the boss and Hooke was the assistant, trapped some gas in a J-tube. Can you see this here? They took some mercury and poured it in a J-tube. This is a J-tube. And capped it, right? So you've got some gas in here. Now the pressure of the gas in there is equal to the difference between these two. The difference between these two surfaces, of Mercury in terms of millimeters of mercury. Okay, right? So you've got some pressure from the outside, which I'm going to call atmospheric pressure right here, right? And so the pressure in here is going to be the pressure of the gas. Okay? So which is greater, the pressure of the gas or the pressure of the atmosphere? Which is greater? Can you see the pressure of the gas would be greater, right? Because it's pushing down harder, right? How much harder? Well, that much harder. There's the difference between the two. So the pressure of the gas is greater because it's pushing that surface down harder than the atmosphere is pushing that surface down. Okay? So what Robert Hooke and Robert Boyle did was they increased the pressure in this gas by pouring mercury on top of there, and that the pressure inside there now, right? The pressure inside the gas here is greater yet, right? You see that? It's greater yet because the difference is that height in millimeters of mercury, okay? How much different? How much greater is this pressure than atmospheric pressure? That much different. Okay? We'll tease this apart more. I want this kind of a graphic is going to be useful to some people, but not everybody. So let's move on here. Let's look at this. Here is another graphic. Suppose that each one of these green spheres represents an atom or a molecule of some gas, right? So these gases are running around here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you can see it's the same amount of gas inside of both of these. But if we have 1 kilogram of pressure, we might have 1 liter, okay? And if we double the pressure on that, 2 atmospheres, by putting an extra weight on there, then we will decrease the volume in half, right? And so we said earlier that P1 times V1, actually that's not the order we did it in, is it? We said P1 V1 is equal to P2 V2. And can you see that that's true here? Look at this. The first one is 1 atmosphere. What's the volume here? 1 liter is equal to 2 atmospheres times what? Half a liter. And you can tell by inspection that that's a true statement. Okay? So this is Boyle's law, and we'll use it now to solve a problem. Oh, one more thing. This is sort of a graph that these guys looked at. You can see that as the pressure is low, here's low pressure here, the volume is high. Can you see that? And as the pressure gets higher, the volume gets lower. I'm not sure if you're familiar with this kind of a curve. It's not linear, right? We didn't expect it to be linear. We knew that volume is reciprocally related to pressure, so we said K1 over P. Remember that? Okay, so as volume goes up, pressure goes down, or as the denominator over here gets big, this gets small, or if this denominator gets small, this gets big, right? So you've seen that before. You've seen that kind of equation before. Okay, so let's solve a problem. Again, Boyle's law is P1 V1 is equal to P2 V2, right? Here's another version of that. Let's solve a problem. As discussed in the opening section of this chapter, you inhale by increasing your lung volume. A woman has an initial lung volume of 2.75 liters. V1 is equal to 2.75 liters, which is filled with air at atmospheric pressure of 1.02 atmospheres. P1 is equal to 1.02 atmospheres, right? If she increases her lung volume to 3.25 liters, V2, right, increases means final situation, right? She increases to 3.25 liters. How do you spell 3? 3.25 liters without inhaling any additional air. In other words, there's no additional air there. What is the pressure in her lungs? P2, right? So P1V1 is equal to P2V2. P1V1 over V2 is equal to P2 because I divide both sides by V2. So now we just fill in. P2 is equal to P1, 1.02 atmospheres. V1, how do you spell 7? 7.5 liters over V2, which is 3.25 liters. The liters cross off. That letter crosses off because it wasn't supposed to be there. And 1.025. I can't do this in my head. I need a calculator. Maybe my son right here will go get me my phone. And I can use my calculator. 1.02, thank you, pleasure, times 2.75 divided by 3.25. 0.863. 0.863, and we're left with atmospheres. Does this make sense? Did you expect it to go up or down? Right? She started out with about the pressure that's in the air right now at sea level. It's about sea level. With a small volume, she increased the volume so the pressure should go down. And that's good. That's correct. Okay. That is good. So I'm going to just look over here and see where we're going next. We are going next to Charles' Law. Okay. So Charles' Law is, we said, volume is equal to some constant, which I called K2 times T, right? Or V1 over T1 is equal to V2 over T2. And this will make sense, right? If you've got a balloon here, and I'm not gonna count these particles. There's what, maybe 15 here. Well, there's particles, the same amount of moles in both of these because it's a closed system. It's a balloon, and if it's in cold water, it's going to be small. Little girl here says it's 12. She counted them real quick. Thank you, little girl. So here, there's 12 particles over here as well. Thank you, little girl. And there's boiling water. And the balloon is resting in boiling water, so the temperature inside here is going to go way up. And it turns out the volume is going to go up too, right? So can you see that I have low temperature, low volume? And it's the same system, right? So if my temperature goes up, what's going to happen to my volume? It's going to go up. That's what this is about. High volume. Okay. So I don't have a story about how these data were collected. I think it was a French physicist who did this, and I'm sorry to say I've forgotten who it was. But we do know that as temperature goes up, volume goes up, just what you would expect. Okay, let me spend no more time on this. Let's do a practice problem. A sample of gas has a volume of 2.0 liters at an unknown temperature. V1 is equal to 2.80 liters. T1 is unknown. Okay? When the sample is submerged in ice water at T2 is equal to 0.00 degrees Celsius, then the volume decreases to 2.57 liters. All right, so we can immediately see something. I'm glad we started with this problem. We can immediately see something here. If we say V1 over T1 is equal to V2 over T2, and we put 0 here, we got a problem, right? So if you suspected that we should not use that because it's not absolute, we shouldn't use degrees Celsius, we should use Kelvin instead, you're correct, okay? So I'm going to say that is 273.15 kelvins. And I'm not going to solve that. I'm going to suppose that you're familiar with that kind of a problem, okay? So we're looking for T1. Well, you know, obviously we can solve for T1 a few different ways. This is going to use a system which I have invented for this class called algebra. Okay, and what I'm going to do is I'm going to switch both of these. I'm going to say T1 over V1 is equal to T2 over V2, right? I just invert. Okay, now that I've done that, I'm going to say T1 is equal to T2 over V2 times V1. And I'm ready. T2, 273.15 kelvins. V1, 2.80 liters. V2, 2.57 liters. The liters cross off and I'm left with kelvins. So T1 is equal to what? 273.15 divided by, you know what, I'm going to multiply by that other guy first. 2.80 divided by 2.57 gives 297.595. 297.595 kelvins. And you know what? I got to do the sig figs here, okay? There's 5 sig figs here, 3 sig figs here, 3 sig figs here. So all I can say is to 3 sig figs. So it looks like this is going to go to T1 is equal to 298 kelvins. Looks like this is roughly room temperature. 298 kelvins. Okay. Okay, so that's Charles' law. So again, Charles' law is the ratio of these is equal to the ratio of those. I think I expressed it as V on top, but you can see that those are both, if the one is true, the other one is going to be true as well. Okay, so let's look at Avogadro's law. So Avogadro's law says that the more moles that you have in a container, the bigger the container is going to be, right? So again, we said that N is reciprocally related to volume. So we said K3V, right? Or that's one way of saying it. Or N1 over V1 is equal to N2 over V2. And that's Avogadro's law, okay? So this is probably, I don't even think the names of these really matter. I think the important point is that you can recognize from a question stem what you have and what you need, right? You've been doing that kind of math for a long time, or those kind of problem solving. So let's do an example. A male athlete in kinesiology research study has a lung volume of 6.15 liters during sleep inhalation. Not sure where we're going with this, but let's say V1 is equal to 6.15 liters. At this volume, his lungs contain this much air. Okay, so yeah, N1 is equal to 0.254 moles. Okay? During exhalation, his lung volume decreases to 2.55 liters. V2, 2.55 liters. How many moles of gas did the athlete exhale? Oh, this is harder than it looks. Okay, so here's what I got. I'm just going to draw one long here, pretend like that's a long. And we're going to say that this is situation 1. Here's the lung in situation 2. Okay? Well, this is how much he had initial total air. And this is the remaining air. I forget the technical term for this, okay? I wish I remembered it. That'd be so impressive, wouldn't it? So this is the remaining air. They're not asking about the remaining air. They're asking about how much he exhaled. Okay. So the remaining air plus his exhaled air, right? So we're going to calculate, first of all, the remaining air and then subtract it from, we know that that plus that equals that, right? So we're first of all going to calculate N2, which is how much is remaining. There's this 2.5 liters. This is 6.15 liters. This is 2.55 liters. Yeah, his lung volume decreases to 2.55. That's it, sure enough. Okay, so we're going to figure out, first of all, how much is left, right? And then we'll go from there. Okay, so N2 is going to equal N1 over V1 times V2, right? I'm taking the Avogadros Law. Let me go back. Let me put Avogadros Law in blue. That might have been a little bit. N1 over V1 is equal to N2 over V2, right? And so that implies that. Let's go back to red. If that's the case, N2 is equal to N1, which is 0.254 moles, times V2, 2.55 liters, divided by V1, 6.15 liters. Liters cross off. I'm left with moles. And this is how much he has left in his lungs, okay? So let's calculate that real quickly here. 0.254 times 2.55 divided by 6.15 equals 0.105317. Did I get that? Let me just make sure I put that in my calculator right. 254, that sounds right. 0.105317 moles that were left. Now I realize I got a sig figs issue here. It looks like there's 3 sig figs here, 3 here, and 3 here. So there's going to have to be 3 sig figs in this number too. 0.105. But I'm not really done yet. I'm not even done yet. That's how much moles was left, right? So I had here, let me go to a different color now. I'm going to go to blue. I had here 0.254 moles of air. That's how much he had in the beginning. And here's how much he had in the end, 0.105 moles. And they're asking how much he exhaled. Right? Do you see that? How much did he exhale? Wow, that's harder than it looks. I mean, someone's going to get sideways with that, I'm afraid. 2.54 moles over 0.105. You see, it's going to be the difference between these two, right? Is going to be that minus that. 4 minus 5 is 9. 4, 1, 0.149 moles. That's how much he exhaled. All right, so I think that's it for this section.